Good afternoon. First off, I'd like to thank the co-authors, Clark Arnold and Steve Van Noort, for their kind assistance and work that has gone into the Van Deemen project. The topic of today's talk, as you can see, is using advanced technologies to more effectively utilize historic exploration data. We'll touch briefly on techniques that were commonly used in the 80s on a project, and then fast forward to what we can do with that same information today. But before we begin, I'd like to ask you all a couple of questions. So, raise your hands. How many of you have used a Brunton, a planimeter? What about a plane table and alidade? Or a hip chain and topophil? What about a light table? A GPS? A portable XRF? What about Leapfrog? Or a mobile field device like your smartphone to collect strike and dip readings or field mapping? Okay, that gives me a good idea of where we all are. And so what do these items have in common? They're all tools a geologist has used in the past 50 years or so to gain insight into the question, what is the tonnage and grade of a deposit, and is it economic? Normally, you'd define economics, in our case, by the price of gold, the mining costs, and percent recovery. But these days, that's just part of the story. You also have to consider government regulations, permitting, access, environmental concerns, and socioeconomic considerations. Technology is changing how we work. This is a screen grab of my phone showing historic surface samples of anomalous gold-colored dots so I can see the geochem values at a specific location. Or I can turn on another layer of a scan of a geologic map and walk up to the outcrop and actually read the notes from the geologists that have been on the ground in the 80s. I can also send claim information from my office to a crew while they're still in the field. Okay, but I digress. I think we all have stories for how we're currently using technology. 30 years ago, the cost of reverse circulation drilling would be in the range of $850 a foot or so. For 1,000 feet, it would cost $8,500 for drilling alone. Times have changed. It can now cost over $35,000 to drill that same footage, assuming that there are no permitting issues. Multi-element trace geochemical analysis is a standard tool in detailed and regional geochemical exploration. In the past, geologists would utilize the top 10% of elemental analysis as anomalous. Currently, affordable trace element geochemistry provides the necessary tools to interpret bedrock geology and mineralization systems. However, a lot of 46-element ICP data resides in company files with limited interpretation. Modern computational tools can rapidly process 3D geologic datasets and assist in generating 3D geologic models. Implicit modeling generates geological models directly from drill hole data using mathematical interpolation functions to generate 3D isosurfaces instead of manual linkage of hand-digitized 2D cross-sections. Many deposits have seen some historic development, whether it is surface sampling, geophysics, drilling, or production. Most current historic data sets are incomplete, with missing drill hole locations, drill logs, assay certificates, level plans, or cross-sections. So, how do you incorporate the past work on a project by people who understood the deposit into a coherent package so you can make an informed decision on the potential viability of the project without having to re-drill the deposit? And that leads us into today's talk. Has anyone been to the Van Deemen? I continue to be amazed at the number of people who have visited the site at some point. The Van Deemen project is located in the northern Black Mountains in Mojave County, Arizona, 50 miles northwest of Kingman, which is historically one of the most prolific gold-producing mountain ranges in Arizona, yielding some 2.5 million ounces of gold. And that number is most likely higher with the current production from the Moss Mine. The Van Deemen property is characterized by Precambrian gneiss and schist, which is overlain by mid-tertiary volcanics and sediments. The two rock formations are brought into contact by a regional low-angle detachment fault with its attendant breccia zone. The top and bottom of this zone is in many cases a sharp contact between broken but not brecciated volcanic and sedimentary rocks above, intensely chloratized and moderately to poorly broken Precambrian gneiss and schist below. The picture is from what is referred to as Area 4. You can see the detachment fault on the bottom with the yellow sericite alteration overlain by the tertiary volcanics. Gold mineralization at Van Deemen occurs primarily in gently dipping zones of quartz, sericite, hematite, pyrite, clay alteration of brecciated Precambrian gneiss. The alteration zones are spatially associated with rocks generally exhibiting an open style of brecciation. These quartz breccias often contain mixed fragment types, including brecciated chunks of vein quartz. The matrix supporting the breccia fragments appears to be made up of finely pulverized rock flour, subsequently replaced by fine-grained quartz. In these quartz breccia zones, sulfides occur in near and late-stage fractures. Mineralization consists of very fine free gold with silica. There are three distinct gold zones at the Van Deemen: Area 2, Area 3, and Area 4. Each gold zone occurs within the brecciated crystalline assemblage along the Van Deemen fault. However, it is also evident that all the gold zones have a pronounced northeasterly trend. In Area 3 and 4, the northeasterly trend of the gold zones appears to be related to the northeasterly trending high-angle deformation zone. Gold production on the Van Deemen mine is believed to date from the 1930s. A section of mineralized rock was mined by open cut. Approximately 350 feet of exploratory adits, along with two shallow shafts, were driven in what is now the central part of the property. More recently, the Van Deemen area has been actively explored for both copper and gold. Copper exploration was done mostly in the 1970s and was directed towards deciphering a highly faulted and sliced laramide quartz monzonite porphyry copper system. The Van Deemen area again received attention in 1979-1980, but this time as a gold play rather than copper, and has essentially been explored for gold since then. As you can see, there has been extensive exploration by experienced mining people and companies. With all the previous work that's been done on the property, you'd think there'd be quite a large database to draw from. Technology in use in the 1980s included using Cooper aerial to fly the area, creating a local mine grid based on a known 0 point. These were XY coordinates with no projection information. High-quality detailed geologic mapping at 1 inch equals 100 feet by Bud Hillemeyer and Jim Faulds. The detachment model represented the current thinking at the time. Fisher-Watt produced computer-generated maps with topography geochem samples. Geochem analysis was usually limited to gold, silver, copper, lead, zinc. In this case, we had gold assays and only a limited number of silver assays that were generated by Amselco. Sectional resource were hand-generated using a 50-foot area of influence. Some of the techniques we will be discussing later were actually developed in the 1980s. For example, Clark Arnold developed techniques as a consultant for Freeport, and I developed statistical techniques for Duval during that same time period. Historic data for this case study at the Van Diemen gold deposit was incomplete, with missing drill hole locations, assays, drill logs, and cross-sections. In 2011, the technology relies on computer assistance, everything from data entry to resource estimation. GIS has replaced the draftsman and light table. GPS units have replaced plane table and allodates. Multi-element geochem packages are the industry standard. Drilling costs have increased. The price of gold has gone up from $288 in 1989 to $1,500 in 2011. Deposits that were not worth looking at in the 80s are economic at the 211 gold price. International Star, a publicly traded company on the OTC markets, took out an option on the property in 2011. Their focus was to demonstrate that the historical exploration data confirmed that the project merited additional work. Towards that end, they hired geographics to create a geologic database, calculate a resource using the 140 drill holes that were available at the time, using the same parameters that had been used in the 1980 resource. The 2013 Czech resource served to confirm the historic resource, and ILST elected to move forward with the project. In 2013, they obtained over 1,000 pulps from the 1986 drilling and surface sampling. The pulps were used to confirm the historic drill hole assays. ILST also collected a bulk sample to check the historical metallurgical results. In 2015, additional information was recovered from the Arizona Geological Survey archives. This included reports, geochem, drill hole location maps for the 1986 and 1989 holes, which added 44 holes to the database. With the additional information, ILST was able to regenerate the resource, engage a mine engineer, Joe Bardswich, who has worked with several other projects in the Black Mountains, to create a preliminary mine cost analysis. So is the project economic? At $1,200 gold, yes. Based on that information, ILST commissioned an SEC Guide 7 technical report as an aid in raising funds to move the Van Diemen towards production. This is a block model with the additional drill holes showing a .014 cutoff. As you can see, quite a bit of the deposit is either at or near surface. In 2017, ILST defaulted on the claims. 3 of us that had worked on the project for ILST elected to move the project forward. What do we have, and how do we move the project forward? We have a company that's made up of a geologist, a mine engineer, and a business manager. We have an incomplete technical report. We have an in-situ resource that has increased contained ounces to 97,000 ounces with no geology. Now, the reason we could increase the resource was based on the additional drilling information, and the variography showed the continuity of 65 feet in a horizontal direction, 35 feet in the vertical, rather than the 50 feet that had been previously used. The deposit is inside an area of critical environmental concern, which requires a mine plan of operation for any additional drilling. We have missing data from over 100 drill holes. We have no drill logs for the 1986 drilling. We have 5 cross-sections, and we have over 1,000 pulps from the 1986 drilling and surface sampling. Newton and Boyle is looking for funding to move towards production. In order to do this, we need to finish the technical report and find some way to include geology in the resource. We can use drill hole pulps to assign lithologic signatures to samples, and we can use that additional information to create a geologic model. And we can assign the Munsell color signature to pulps, and we can look for a gold signature. We focused on the pulps from the drilling. The pulps were rebagged prior to further work. There were 932 samples, plus standards and blanks, that were analyzed using the Olympus Delta handheld XRF in geochem mode. 38 elements were analyzed. The Munsell color code was designed as a visual color system for classification of rocks, sediments, and soil. Steve Van Noort found this to be very useful at Picacho. So what we did was we took pictures of each pulp sample with a smartphone, and we used an app on the phone to assign color to the sample. From there, we created a database with the drill hole information and the color codes. The main goal of statistical analysis was to find a way to use the geochem analysis from the portable XRF to classify the data by known lithology. I used IOGAS software developed for geochem data analysis. Its advantage over standard statistical packages such as SPSS, Statistica, or Excel spreadsheet add-ons is that it has additional useful tools such as classification diagram and the tool that I was interested in, specifically the discriminant projection analysis. It also reads XRF data and integrates with the Discover software platform that I was using to manage the data. As with any statistical application, there are certain rules that must be followed to optimize your results. For example, in order for a data set to be used for statistical analysis, it is assumed to be taken from a random population that's normally distributed, and it's assumed that the sample set that we're working with actually represents the population that we are describing. There were 24 elements with most values above detection limit, and this is including gold from the 1980 assays. The first thing to look at in the data is the distribution. It's common for elements such as gold, copper, lead, zinc to show a log-normal distribution, such as elements such as aluminum, calcium, potassium, sodium to show a normal distribution. Looking at the distribution, that is apparent here. Now these histograms are colored to reflect known lithologies in our sample set, with the black values representing unclassified lith values. This slide shows the elements transformed to log values, and you can see an improvement in the distribution of some of the elements, for example, copper. Based on a visual inspection and the skewness kurtosis values, 16 of the elements were transformed to log values for further work. Next, I created probability plots of the elements. What I'm looking for here is an indication of the number of populations I may be dealing with and what's happening with the left and right tails of the plots. If the data is from a single population, the graph should be a relatively straight line. If there are bends or breaks in the line, then it gives me an idea there may be several populations present. Flatline tails on the left side shows me the number of samples at or below detection limit, and scatter at the top of the right tail may indicate an additional population possibly related to mineralization. Discriminant analysis technique creates a set of rules to assign a sample to one of a set of groups. In order to come up with these rules, a training data set is used for which the group memberships are known ahead of time. So I had 14 holes from the 1986 drilling with lithology derived from cross-section, and that was my training set. In total, there were 289 lith values with 4 lithologic classifications. QT only had 3 values, and that was eliminated from the data set. TBA, the tertiary volcanics, had 8. PCA, the Precambrian acidic gneiss, had 211. PCS, the Precambrian mixed gneiss and schist, had 67 values. Discriminant projection analysis is similar to principal component analysis in that it tries to maximize the variance between groupings, except here we already know what our grouping variables are going to be, in this case, lithology. The projection step uses the training data to calculate linear discriminant functions, which are linear combinations of the original variables that maximize the difference between the predefined lithology groups. Discriminant projection 1, or DP1, calculation is a combination of elements that explain the majority of the variance of the population. DP2 explains the next amount of variance, and so on. It creates a value for each discriminant projection, in this case DP1 and 2, for each data point. These functions allow the samples to be plotted in discriminant space, so group separation can be visualized and investigated. The graph in the upper right hand of the screen displays a scatter diagram of discriminant projection axis 1 versus DP2. TBA samples are in blue, PCA samples in red, and PCS in orange. You can see the tertiary volcanics separate well, except for one lone sample, from the Precambrian units, while in the Precambrian units there is some overprinting of the acidic and gneissic units. The upper left displays the same graph with a classification colored in background. So any new samples that fall within the blue area would be classified as tertiary volcanics. The lower left probability plot for all data is colored by lithology. In this case, DP1, you can see the TBA samples shown differently than the Precambrian units. In the lower right, a split probability plot subdivides the data according to the color attribute groups, in this case lithology, and plots a normal probability plot for each group for the selected variables on the same diagram, with the respective colors from the attribute dialog. You can see in this case, DP2 is doing a better job of separating the lithologies. Once we had the calculations from the training set, we applied those calculations to other samples. IOGAS classified 640 samples with unknown lithologies into 3 groups based on the training set parameters. The tertiary volcanics contained 239 items, PCA contained 145, and PCS contained 256 items. This diagram shows DP1 and 2 on the X and Y axis, similar to what was shown in the training set. As you could see, it did a fairly decent job of classifying the unknown values. However, there is still a bit of scatter with the samples in each grouping. This is the split probability plot for DP2, and again you can see that there is a visual difference between the lithologies. So now I'm fairly comfortable with the results. However, I do need to check those results. So 640 samples were checked against the known database of lithologies and the Munsell color designation. Discriminant function only classifies against grouping it knows. If there's a lithology that is not in the training set, it will continue to classify it as best it can. Several holes did show discrepancies. Hole 31 in Area 2 was near a quartz monzonite porphyry intrusive, and the pulp was a relatively light gray in color, so I'm thinking those values could be from the intrusive. In Area 1, PCA and PCS order were reversed in the drill holes. These are exploratory holes outside the resource areas, and it could possibly indicate a new lithology. In all, 32 drill holes were added to the database, and that data was merged with the existing lithologic database. So now I have a database with additional lithologies that I can use to create a geologic model. It seems that everyone wants to jump onto the implicit modeling bandwagon. Implicit modeling uses mathematical tools to derive the model from the data. A definition from the Micromine website says that an implicit model is a continuous mathematical representation of an attribute across a volume. This method is not only efficient, it eliminates the personal perceptions and interpretation of geologists because it is a numerical process that is free of bias, which means less subjectivity and greater reliability. Traditional modeling methods, those relying heavily on manual digitizing, are called explicit modeling. Implicit modeling techniques were used to create a 3D geologic model of the deposit. We used Leapfrog to model Area 3 and 4 separately from Area 2. Those results were then tied back to historic observations and existing cross-sections to confirm the validity of the model. We modeled just 3 lithologies: the tertiary upper unit, shown here in green, the detachment fault, shown in red, and the Precambrian basement, shown in brown. You'll see that there are also yellow quaternary units displayed in some of the drill holes. We started out using only the surface geology and drill holes to create the model. We did include strike and dips from the historical mapping. We then cut sections along the same section lines as the four historical sections we had previously recovered. The results showed marked dissimilarities in contacts between the units. To resolve the discrepancies, we digitized the boundaries on the sections back into the model. The result was more in line with what was encountered in the drill logs, sections, and diagrams in the reports. Area 2 was more complex to model. We had the same lithologic units as Area 3 and 4, but we also had faulting that ran through the area. We modeled each of the fault blocks separately. Once we'd resolved the issues involved with merging the surface geology and drill holes, Leapfrog did a good job of handling the fault blocks. As of September 1st, that's what we've done up to this point to move the Van Diemen forward. There is still more to do. Our goal is to move the project forward towards production. As far as science goes, I need to see if we can tie the Munsell color assignment from the pulps to lithology to gold values to predict gold mineralization. This is something Steve Van Noort was able to do at Picacho, and I'd like to do additional multivariate work with the geochem data to see if I can get alteration signatures and test if that's important for mineralization. I need to also update the resource to include the geologic domain. Once that's complete, we can create a preliminary pit design, and from there it involves a mine engineer to move the project forward. So what have we learned from this? What are the conclusions? We need to try and find as much information as possible so you don't have to regenerate it. As we said earlier, 30 years ago, cost of reverse circ drilling would be in the range of $8.50 a foot, and it can now cost over $35 a foot or more, and there may now be access and permitting issues. The Arizona Geologic Survey provides a wonderful service with its document repository. Statistical techniques need to follow standard practice. We need to treat each data set separately as they are different. We need to check our data to confirm the results. This applies to everything from data entry to modeling to resource estimation. The implicit modeling needed the addition of historic cross-sections to refine the model. While these techniques provide tools to aid in interpretation, they are not a replacement for field observation and understanding the geology and mineralization of the deposit. Thank you for your time. For additional information or questions, please feel free to contact me at 520-275-6173 or bcarroll at geographics, GEOGRAFX, world.com.